So first, I would like to present you some our last results on time-in-a-box simulation of penetrative convection. That's a work I'm doing with Axel and Wolfgang. So that's the first, my first attempt with a pencil code. So the plan is very simple. I will present something on some notes on penetrative convection. Our previous works in local slab geometries with another code, and now our global simulation. That's okay. Yeah. First, this beautiful picture. Maybe it will be a good place for an expensive code meeting. In Toulouse, it's my observatory. My lab is in Toulouse, and this observatory is linked to my lab. So that's biggest telescope, French telescope in the country. It's a 2 meters telescope here. This is for television. And yes, and we can visit, public now can visit the place, and that's very, very beautiful. And now I'm doing some observation here, example, at the end of the month, on a fully convective star. So, what is penetrative convection? So, here, it's on this graph, here we have convection zone, and here we have a radiative zone. Okay, and at the interface, we know that the temperature gradient should be the adiabatic one. Below, above in the convection zone, it's a super adiabatic gradient, and below it's a sub-adiabatic gradient. Okay, and the mixing length theory says that the velocity of a blob, of convective blob here, which is cold compared to the surrounding medium, this blob falls down. Okay, and its velocity is related to it's the temperature contrast compared to the medium. Okay, and the mixing length theory relates the velocity of a blob to the kinetic energy of the blob to the Archimede force, which involves the mixing length L. L is called the mixing length, which is some multiple of the local pressure scale height. The convective flux is this one, which is a correct expression, no assumption. Okay, and in the mixing length theory, the temperature contrast of the blob is related to the super adiabatic gradient, which means the local adiabatic temperature gradient minus the adiabatic one. And you see that one can see that if delta t equal to 0, okay, it means that the convective flux is 0, and then it means that the velocity is 0. And delta t 0 when the temperature gradient becomes the adiabatic one. Okay? So that's the Schwarzschild criterion. It means that normally the blob should stop here in the mixing length theory. Okay? But delta t equal to 0 means that the Archimede force is plus the gravity force is 0. So the acceleration is 0. But acceleration 0 does not mean that velocity is 0. Just acceleration. And then by inertia, the blob penetrates into the radiative zone. Okay? So penetrative convection is not predicted by mixing length theory, but in reality there is some penetration in the radiative zone. Okay? And what is interesting, it's the coupling between the penetration of the blob here in the stratified zone and the generation of internal waves. Because the blob has some kinetic energy then, and the blob is broken by the Archimede force, which is, in this case is like that, and this kinetic energy should be given to the medium, and is given in the form of internal waves. Some part is given in the form of internal waves. And the K parameter which governs the penetration is the Pecke number of the blob, which is the ratio between the product of the velocity of the blob multiplied by the length scale of the blob, typical scale of the blob, divided by the radiative diffusion. Okay. And in fact, there is two regimes of penetration. One which is called penetrative convection, or penetration, and the other one is overshoot, which is not the same in fact. Overshoot and penetration are not equivalent. Overshoot is correspond to regime where the Peclet number is around unity. And in this case, if the Peclet number is around unity, the blob penetrates there is a large penetration. Okay? If here the Peclet number of the blob is unity, it means that the blob will thermalize very fast with the medium. And then the blob does not feel the Archimedes force and then penetrates over large distance in the radiator zone. Okay? So Peclet of about unity means overshoot. And overshoot means large penetration. Large penetration. Okay? But if the Peclet number is very large, the blob keeps its identity compared to the medium because it don't lose by radiation its temperature excess. And then the blob feels strongly the Archimedes force. And then the penetration is very small. The penetration is very small, so that is called penetration. Okay. And some people had adiabatic penetration because in this case the temperature gradient is locally completely changed by this penetration, and the temperature gradient becomes adiabatic one. Okay? Which means that the convective zone is deeper compared to the one without penetration. Okay? And once the Peclet number of the blob become unity, okay, we have okay. So there is two penetration regime.
So even in overshoot, you will retain the identity of the blob because you may equilibrate the temperature, but then the density becomes all the same.
It's the same. It's related. Density and temperature are related.
But then why do you call it? Why does it penetrate them? It's just a bit of the gas which is just having a different velocity.
Yeah. So.
And how is the upward thing established?
Hmm?
I mean, if all this stuff is going down, let us say,
Yeah.
then there must be some equal mass flux coming back to maintain
Sure.
equilibrium.
Yeah. And the guy, it's Jean-Paul Zahn.
He was asking how it is established. He was asking you a question how it's established, but of course the flow is flowing up, so there's some circulation, of course.
Yes, in compressible convection, I will show you the topology of compressible convection is shaped by plumes, downward plumes, which are very narrow, and the return flow is more larger.
Yes, but even in the overshoot layer, there's a return flow.
Yes, sure. Yes, sure. You have to keep the mass flux.
It's convective everywhere. So there is zero mass flow and finite, because of stratification, a finite velocity, mean velocity. It's a necessary thing.
And the theory of the S2 regime has been made by Jean-Paul Zahn in 1991. And of course, in the sun, the Peclet number at the bottom of the convection zone is very large. So we have first adiabatic penetration and then overshoot. So,
And by the way, in the adiabatic regime, does it actually mean that the entropy gradient is
it's flat. It's flat. Something like that.
Exactly flat or is it slightly stable?
You have that. Normally, without adiabatic penetration, you have that. Okay, that's adiabatic. That's the entropy gradient, which is flat in the convection.
No, not exactly. It's slightly not flat, of course.
Hmm?
It's slightly not flat.
It's slightly self-adiabatic.
Yes, because the flux, the convective flux, is proportional to the finiteness of the gradient.
In the mixing length framework, but in reality. And then, if you have adiabatic penetration, you have that. The entropy gradient remains zero here, and then you have the radius.
Yeah, but I was interested in the slight departures from zero. So I believe what it is this. It's slightly stable, and it's unstable here, of course. And here it's slightly stable.
Yeah.
And then, so here it's negative, and here's
Here's a gradient is positive.
Here positive.
Here it's negative.
Negative. Is weakly negative.
And you would actually, what do you call the bottom of the convection zone?
Normally, if you have adiabatic penetration, the bottom is there.
If they what?
The bottom of the convection zone is there now. If you have adiabatic penetration, if the Peck number is sufficiently large. So we investigated the coupling between the penetration of plumes, convective plumes, and the generation of internal waves in the radiative zone. And that's very important from an astrophysical point of view, because as Natalie showed us before, for example, in the Sun, the rotation of the core is almost uniform. And you certainly know that to obtain a uniform rotation profile, we have to extract angular momentum in the core. You know? So we have the Sun, we have the core, and we have convection there, 1/3. And here the rotation is almost constant. And then it's very easy to transport angular momentum in the convection, simply by convective motion. And then once the angular momentum is there, the angular momentum lives following the magnetic line. Okay, that's a magnetic braking of the Sun surface. But the problem is to transport angular momentum from here to here, okay, to the bottom of the convection zone. And one way to do that are internal gravity waves, because waves can transport angular momentum. In fact, a wave transports angular momentum from one place to another place where she is dissipated here. When the wave is dissipated, the angular momentum is given to the measurement. So the standard model of the Sun does not incorporate angular momentum transport by wave, but that's one thing we should be having now. The problem is to find the spectrum of these waves and their amplitude. Another important thing with the wave.
What generates the waves?
Hmm?
What generates the waves?
The waves are generated by two mechanisms are possible. The first is plumes, convective plumes, like a hammer, it knock, and then waves are generated here. Another mechanism which has been proposed is related to shears, because at the bottom of the convection zone there is a tachocline. Tachocline means strong shear. Okay. So here is convection and here is tachocline. And when one has a shear above the stable zone, some part of the kinetic energy included in the shear can generate here waves. So that's another mechanism which has been proposed. But in our case, we are interested in this mechanism by two. So we did that in the past using the Stein and Nordum code, one version of the Stein and Nordum code, a lot of versions, without radiative transfer. And then what we did is local investigation of the wave generation at the bottom of the convection zone. So the equations are there. So constant gravity field. In Stein and in this code we worked with the internal energy, and at the top of the domain we imposed a cooling term to force the convection. So the gas was monatomic. The boundary condition was periodic in the horizontal direction, here and here. And in the vertical direction we apply straight-free boundary condition for velocity, constant temperature on the top because of this cooling term, and constant flux at the bottom. And Hawke's code was a 6th-order compact finite difference code for the spatial derivative and 3rd order in time. So that's one typical numerical simulation in 2D of penetrative convection. So here it's a convective zone. I can show you another tack. Okay. So here it's convection zone. Here. And above a cooling zone, okay, and below here the radiating zone. And at the beginning we put an entropy bubble to accelerate convective instability.
So what is color coded is entropy.
So it's entropy, sorry. Yes, that's entropy. And then the bubble will fall down and accelerate the convective instability. Cool. And then one can see that some plumes, downward plumes, okay, which normally in the mixing line framework the plumes should stop here, but one can see that the plume penetrate in the radiative zone. And the question is, what is the gravity, the internal wave field which are generated here? So first we can make some diagnostic. So for example the fluxes. So here it's the depth, means that the depth go to 0 here, below the, at the top of the convection zone to 3. So here it's a convection zone between 0 and 1, and here the radiative zone between 1 and 3. And then we have, in this case, I plotted just 3 flux, the radiative flux, the convective flux, and the kinetic flux. And then we can show that the kinetic, there is some non-negligible part of the kinetic flux, because the downward plumes transport kinetic flux in the bad direction. And then in the radiative zone, the flux is transported by radiation, of course. And once we are in the convective zone, the flux is almost mainly transported by convection. And normally, in the MLT theory, the convective flux is 0 at the bottom of the convection zone. But we see that is not the case. The convective flux is not 0 at the bottom, it's still positive, reverse, and then go to 0. And this is the penetration below the convection zone. And one way to quantify this penetration is to compute the time evolution of the first 0 of the kinetic flux. That means that we try to find where the kinetic flux goes to 0, below the convection zone. And this distance between the bottom of the convection zone and the first 0 is defined as the penetration. And in this case, you see that the penetration is around 0.6. Compared to the convective zone, which whose depth, the width is 1, it means that we penetrate more than half of the convective zone. It means that we are in an overshoot regime because the penetration is very large. And indeed, if we compute the Peclet number of the flow, in this case it's not really the Peclet number, simply the ratio between the RMS velocity and the radiative diffusion. We should multiply still by the typical length of the plumes to find the Peclet number of the plumes. But we see that below at the bottom of the convection zone, the Peclet number go down very fast. So in this case, it's around 10 or 20. But if we multiply by the width of the plume, it's around unity at the end. So the Peclet number is around unity, which means that the block thermalizes very fast here and penetrates in the radiative zone over a long distance. Okay. And then the question at that time we had, what is the wave here?
If it has thermalized and it has attained the same density as the surrounding,
yeah.
then why isn't it shed apart as it penetrates?
Why?
Why there is no instability as it moves down? Like Kelvin and moles or something.
For the
Because the shear is too weak in this case. The velocity of the block is not very large compared.
But you mean
Yeah.
in the unstable layer, right?
Yeah.
I think the resolution is also so high. If you had much more resolution, then
Yes. If you have larger Peclet number, you can have secondary instability here along the plumes. So we developed a new way to measure the internal wave in hydro simulation. And our method was very simple. The idea is, if I have internal wave which propagate in a box, they will correspond to the eigenmode of the box. So we first compute the eigenmode of the box, and then we project the velocity field of the simulation onto that eigenmode. And then we get the mode amplitude. So to do that, we dealt with the anelastic approximation, which is useful to remove the acoustic wave in our model. So that's anelastic equation for one mode. So it means that we have to compute an eigenvalue problem, so eigenvalue with associated eigenvalue. So that typically is a Brand-Weissler frequency profile. So Brand-Weissler frequency is almost zero in the convection zone, and it's positive in the radiative zone. Yeah. And then here that I showed you some eigenmode of the radiative zone. So that's the vertical displacement of one gravity wave, gravity mode, okay, and that's the horizontal displacement. And what you see is that here we are at the bottom of the convection zone. The modes go down because the gravity mode cannot propagate in the convection zone. Okay? And then the idea is very simple. We take the velocity field of the simulation and we project this velocity field onto the eigenvector. And we get the amplitude coefficient, which is called the projection coefficient. And for example, if the mode omega kn propagate, it means that this coefficient should behave as exponential I omega, as a normal mode. So for example, I show you, so this coefficient is complex
But
one.
some of the velocity is just due to the penetration. So not all the velocity are due to waves.
Yes, that's not a complete basis in this case. You have some other contribution coming from the convective velocity,
Yes.
acoustic mode, or something like that.
Yeah.
But in our case, we just want to keep the internal wave part of the velocity field.
So that's a way to simply diagnose how much is in the waves.
Okay.
So that's the time evolution, for example, of the projection of on the mode L equal 1, N equal to 0. It means that it's a mode with horizontal dependence of the form like that, okay, and with no node in the vertical direction. Okay. So the solid line are for the real part of the projection coefficient, and the dotted line are imaginary part. And then we see some oscillation of this coefficient. And when then the real part and imaginary part behave as cos omega t and sin omega t, it means that we have an eigenvalue which propagate. Okay. So for example, if we take the Fourier transform of this signal, okay, we get this one, the peak. That frequency, that's the power spectrum, and we get a peak, which is around 0.25, 27 in this case. And this peak corresponds to the eigenmode, so eigenvalue of the eigenvalue corresponding to the eigenmode L equal 1 and L equal 2. So in this case, we extracted in the simulation this mode. And that's a comparison to the classical wave. Classical wave in this case means that we take the velocity field, we do a Fourier transform in space, then a Fourier transform in time, and we look what's happened for L equal 1, and we get progress of peak. It means that in this peak there is a lot of modes. In our case, we are able to extract one mode in this forest.
So can you say it again? The right picture was obtained by just taking the velocity
So,
at one point.
No, the wall velocity. You take the vertical max flux, for example, x, z, t. We do a first Fourier transform in space, k, z, t, and a second one in time, k, z, and omega. Okay, and then you look in this space, z and omega for k equal 1. You look where are the peak in the radiative zone. Okay, and you integrate in depth for every frequency, and when then you have a peak, okay, you have here a peak in the spectrum. Okay. But in this case, you take the whole mode at k equal 1. For the mode at k equal 1. So n of 0, 1, 2, 3, 4, 5, etc. And then it's very difficult to do a quantitative, not qualitative, but quantitative study with that kind of spectrum. Because everything is mixed. So that's some kind of an example of result we obtain with Opus code. So now